Continuing with section 6.2, we are looking at example 3. It says sketch a right triangle that has angle theta and find the other trigonometric ratios. So one of the ratios is given and we have to find the other trigonometric ratios. Now in the chapter 5 there were problems where you would be given information about one of the trig function. So for example, there was a problem something like sine of t is equal to 4/5, and then they mention that cosine of theta is less than 0, or they could say theta terminal side of theta or terminal point of theta is in quadrant 2 or 3, or some information like that. So then based on those you had to find all the rest of the trig functions. So what you used in there were identities, that actually mainly Pythagorean theorem. Okay, so the Pythagorean theorem, there are kind of 3 sets of equations in the Pythagorean theorem, but the most common, most important is the one I wrote here, that sine squared theta is plus cosine squared theta equals 1. Now you must remember this theorem or this result, because this will be helpful in many places. So in here we will do the finding, we will find the these trig ratios using a triangle, and those questions in chapter 5 that I am referring to, those can also be now can be done by using right triangles. I will show you later. I think they come up in chapter 7. So cosine theta is 9/40. So what we do, we will make a triangle like I did over here. It can be any, you can draw it in any way. You can have it like this, it doesn't matter. So one of the sides is 9, leg is 9, and we will call that the adjacent, so it means it should be the side which is adjacent to theta. We don't know the value of theta, but it's okay. So let's say this is theta, then this side has to be 8, and the 40 goes with the hypotenuse. Okay, and now we have to find the other leg or other or the opposite side of so we will find the opposite side using the Pythagorean theorem, and I found it to be square root of 7 times square root of 31. So now we can just use the SOHCAHTOA and write down our identities one by one. So what I did here is, this is cosine theta. So in front of it I wrote secant theta, because secant is the reciprocal of cosine. So you just flip the fraction and you get it. So sine of theta is 7 into square root of 31/40. So we have 40/7 into square root of 31. But in this case we have to rationalize. So multiply by square root of 31 top and bottom and simplify, and we end up getting this as our answer. I have not shown the rationalization here, but you must show it in at least one place. If it is occurring in more than one places, you don't have to show it in every place. So tangent of theta is 7 into square root 31/9. So cotangent theta will be 9/7 into square root of 31. So I multiplied by 31 square root top and bottom, got this, which can be then simplified to this result. Similarly, you can do you can see how I did this one. So we were given the cosecant theta was given, and we make a triangle. We can put our, if you remember what 13 corresponds to and what 12 corresponds to, but I think we are more used to sine, cosine and tangent, so I will write the value of sine theta by flipping the fraction for cosecant theta. So get sine theta is equal to 12 over 13. So now the triangle I made actually doesn't fit with the values, but doesn't matter much, although I think it should be more like this, and theta is here, then 12 is here, and 13 is here. And so now by using the Pythagorean theorem, I find A, the adjacent, which is coming out to be 5. So I put A here, and then we have that A is equal to 5. Now what do? Just write down the trig ratios. So here on this, from here I went there, wrote all the trig ratios. Okay. Now next thing we are going to do is look at some special triangles, and this is something I did mention in class. I don't know if some of you might remember. So if we have a isosceles triangle, and we can see, okay, I think it should remain like that. Okay, an isosceles triangle is one in which two sides are same. In an isosceles right triangle will be the one in which both legs are of same length. So this length, this leg, and this leg, they are of same size. Okay, and now these angles, they are both 45 degrees, because if you recall, we saw that the sum of these two angles will be 90. Okay, so this is alpha, this is beta, so alpha plus beta is 90, but alpha is equal to beta. Why? Because the sides are same, then opposite angles will be same. Okay, so if you put now, replace alpha by beta in the equation here, so we get beta plus beta is 90 degrees, so that 2 beta is 90 degrees, so then beta is 45 degrees. 90 over 2 is 45 degrees. So if that is then alpha is 45 degrees. Okay, so this angle alpha at beta, or which is the same as pi over 4. So this is the same as pi over 4. And so now what do we do with this information? So we can now find out what as cosine of pi over 4, sine of pi over 4, and all the other ratios for pi over 4. So how do I do that? Well, we said these two sides are same, so if this is A, then this is A. Now just for simplicity, we can take them equal to, because we are trying to find the trig ratios, so I can just take this one and this as 1. So if these are two are 1, I should be able to find the length of the hypotenuse. So we want to call it h. Okay, so then h square is equal to 1 square plus 1 square, which means 1 plus 1, which means 2. What does that tell us? That h is equal to square root of 2. So when I know that, then you can easily see. I will erase this piece. Okay, so you can see that cosine of pi over 4 will be equal to 1 over square root of 2. We rationalize and we end up getting square root of 2 over 2. Similarly, you can find the sine pi over 2. So sine of pi over 4 will be equal to same thing, 1 over square root of 2. So it means it is square root of 2 over 2. And now tangent of pi over 4 is 1 over 1, opposite over adjacent, so it will be 1. And now you should be able to write other three trig ratios. Now we come to the next type of triangle, which is the equilateral triangle. So what is the property of an equilateral triangle? All three sides have the same length. So the angles will also be of same length, same measure. So what will that be? They are all same. So you can do that. Let's say all of them are alpha. So alpha plus alpha plus alpha is 180. So 3 alpha is 180. So alpha will be equal to 180 over 3. 180 over 3, which is 60. So each angle is of 60 degrees, or pi over 3. Radians. Knowing that, I'm going to do this. So I'm going to take each side to be equal to 2, because the sides are same. So we can take any number. We can take 5, we can take 10, we can take 1, we can take any number you think of, but 2 will make sense in a minute. So let me take 2, 2 and 2. Okay. Now then what I do, I take from the top vertex C, I draw a perpendicular at the bottom. What this perpendicular will do is it will divide the triangle into two pieces. So in two right triangles. One is here, the other is this. So two right triangles. And in each right triangle, so let me pull out one of the right triangle here. Looking something like this. This is a right triangle. This angle didn't get disturbed, so this is still 60 degrees or pi over 3 radians. But this, the angle at the top, this got bisected or divided into two equal pieces. So it was 60 degrees. So it means each pieces, this and this piece, each is 30 degrees. So this is 30 degrees or pi over 6. Okay, what happened to this side? This length stayed 2, but what happened to the base? Well, remember we got the triangle divided into half, so it means this side will be the same as that side. So the total was 2, so now half of it is 1, so this is 1. So now let me remove this information for a few minutes. Okay, so now with the sides you can see our shorter side is 1 and the longer side is, or the hypotenuse is 2. So I should be able to find this side. This, you can say, you're talking about 60 degrees, so this will be the opposite side. So how do I find the opposite side? Well, I use the Pythagorean theorem. So O square plus, so this is not 0 by the way, this is O, or if you want to call it H, that's fine. I mean, H becomes height A, you want to call it A or B, that is fine, but let me see, O square plus 1 square is equal to 2 square. So O square, I think it's confusing, someone might think it's a 0, so let's give it another name. I'm going to call it a B. Okay. So B square, so B square plus 1 is equal to 4, so B square is equal to 3, so B will be square root of 3. Remember, again we are discarding the negative sign because this is the length. Okay, now that we know, so now we have this situation. We have a triangle, this angle is pi over 3 or by 60 degrees. This side is 1, this is 2, and this is square root of 3. So the opposite is square root of 3, adjacent is 1, and hypotenuse is 2. So you should be able to write all trig function ratios for this one. So we get sine of pi over 3 equals square root of 3 over 2. Okay. Cosine of pi over 3 equals 1 over 2, and tangent of pi over 3 equals square root of 3 over 1 or square root of 3. Now from the same triangle, if you know it, you can actually find or write down the trig functions or trig values, ratios for the pi over 6 angle as well. So pi over 6 is that. So now you will have sine of pi over 6 is equal to, so now the opposite is 1. So this will be 1 over 2. Cosine of pi over 6 will be square root of 3 over 2. So note what was cosine here became the value of cosine of pi over 3 is the same as value of sine of pi over 6, and so on. The same thing, the sine of pi over 3 is the same as cosine of pi over 6, and then the tangent of pi over 6 will be, so it will now be 1 over square root of 3, which when rationalized gives you square root of 3 over